Hey there, welcome to another video. So in this video, we're going to talk about how to solve some equations with trigonometric functions in them. They're honestly not that bad, there's just really two things we need to understand about them. Three things. Number one is that in order to solve equations, you need to isolate something. And so we're going to use techniques to isolate our trig functions. Number two, once you've done that, try to use your unit circle. The third thing, because we are not using inverse trig functions, do not restrict your unit circle. So we're isolating, using unit circle if at all possible. If it's a weird sort of thing that your function is equal to, then no, we can't. But if it's anywhere on unit circle, man, we're in good shape. And number three is that do not restrict this. Like we did with inverses, you don't need to do that because we are not using those inverse functions to do this. We're using unit circle and we get more available solutions that way for this on that unit circle. The last one, kind of hidden thing, is that most of the time we're finding all the solutions between 0 and 2 pi. So on one revolution of that unit circle, we can find a general solution. I'll show you how to do that in the first example, but normally we find all the solutions within a certain interval. Because these things are cyclical, they go forever and ever and ever. We really don't find all solutions all the time, just on a certain interval. And that also leads to one more thing. That's like 5 things, sorry about that. Is that if ever the argument of your trig function is different from just theta, we're going to have to manipulate our period a little bit. I'm going to show you exactly how to do that too. So let's get right into it. So number one thing, whenever we're solving any equation, normally we're just isolating a variable. Well, in this case, in order to get to that variable, in order to get to theta, we have to isolate our trig function. So isolate your trig function first. We're going to do things like in the first example, like subtracting 3 and dividing by 2. So if we subtract 3, we get -1. Divide by 2, we get -1/2. Now, once we've isolated our trig function, use your unit circle. Now you can go ahead and think of this like an inverse, but do not restrict your domain. So I know that sine inverse is only from -pi/2 to pi/2. That's true. But normally we're looking on 0 to pi for our trig function. We're going to answer this question like, what angles cause us to have a y-coordinate of -1/2 on the entire unit circle on one revolution? And so there's going to be 2 solutions here. So we're thinking sine of theta equals a y-coordinate on the unit circle. Let's find that y-coordinate of -1/2 and how many angles gives me that. So if sine theta equals our y-coordinate and we're looking for -1/2, that's there and there. So our y-coordinate is -1/2 here and here. So sine of 7 pi/6 would give us -1/2 and sine of 11 pi/6 will give it -1/2. Notice what I'm not doing. I'm not using -pi/6. This is almost always from 0 to 2 pi. That's typically what we like to do. So we're not using it like sine inverse. That's probably the biggest thing that students get confused on because we just talked about inverses for a really long time. And now we're going back to, yeah, let's use the whole unit circle. And that's exactly what we're doing. So we're going to say, hey, in order for sine of theta to equal -1/2, theta would have to be 7 pi/6 or 11 pi/6. Those are all the solutions on this interval of 0 to 2 pi. All that means is that those are the 2 angles on that one rotation, that one period of sine, for which we're going to get this y-coordinate of -1/2. And it's pretty clear. Sine of 7 pi/6 is -1/2. Sine of 11 pi/6 is -1/2. Those are the 2 solutions. Now, if you need to show all solutions, we know that every time we make a full rotation, all of our y-coordinates repeat. All of our sine thetas repeat for every period that we traverse. And so if we wanted to show that for all general solutions, all we really have to do is take these two values, both of them, not just one of them, take those two values and add 2k pi to them. What that means is that you're going to hit 7 pi over 6, and if you add 2 pi, you're going to hit it again, just after one full revolution, and then again and again and again, and same thing 11 pi over 6. You'd be here, add 2 pi, you're going to go around again, be at the same place, around again, be at the same place, and we can show it like this. Just take your solutions and add 2 pi. Now we throw a k in there to say, yeah, you could go positive revolutions or negative revolutions and still end up at the same exact point on your unit circle. So if those are the two angles on one revolution in a circle that give me this y coordinate of -1/2, then if I add rotations to that or subtract rotations, that's what the k does. It says you can add a certain number of rotations, full rotations, or subtract them and you're going to end up at the same point. This would be our general solution. So this is all of the values, every one of them forever, that would possibly give you a y coordinate of -1/2 on the unit circle that would solve that equation. That's really all there is to it. So we're isolating using the unit circle. Typically what we do is we normally just stop here because that's usually what they ask for, is find me all solutions from 0 to 2 pi. And that's pretty much all that we're going to be doing here. So let's move on to the next one. Let's actually do that one. So 4 cosine squared theta minus 3. Isolate your trig function as much as you can. So we're going to add 3. We're going to divide by 4. So if we do that, if we add 3 and divide by 4, remember, we do have to isolate. So cosine squared equals 3/4. That's our first step. But cosine squared means cosine to the second power. How in the world do we undo power 2's? Well, we take a square root and we take it on both sides. And we use a plus and minus. So square root of a power 2, those things cancel. We're going to get cosine theta. When we take the square root of 3, we're going to leave that, but the square root of 4 is 2. We also have that plus and that minus, and so we're actually going to get 4 solutions here. Now this is a little weird. Most of our trig functions are going to give us 2 solutions on a unit circle. Do you remember that power 2's typically give you 2 solutions? Like usually for polynomials. Now this is not polynomial, but it is going to bear out that way. Because that square root yields a plus and a minus, we're going to get 2 solutions for cosine theta equals positive square root 3 over 2, and 2 solutions for cosine theta equals negative square root 3 over 2. So we've isolated, and now we're solving. We're in the process of solving. So once we've isolated our cosine, we're going to have cosine theta equals positive and negative square root 3 over 2. Use your unit circle. So we're going to take a look at cosine theta equals square root 3 over 2. Remember that cosine theta is equal to the x coordinate. So all we have to do is go to our unit circle. Do not restrict your domain to 0 to pi. That's not the idea here. On the entire interval of 0 to 2 pi, find out what angles give you a x coordinate of square root 3 over 2. Cosine theta equals x coordinate. So we're just going to find that. So x coordinate of square root 3 over 2 is here and there. So not negative. Remember, we're on 0 to 2 pi. So x coordinate is pi of square root 3 over 2 gives us pi over 6 and 11 pi over 6. Cosine theta equals square root 3 over 2 on 2 angles here, pi over 6 and 11 pi over 6. We do exactly the same thing for cosine theta equals negative square root 3 over 2. We understand that cosine theta equals the x coordinate. Let's look for this particular x coordinate. It's going to show up 2 spots here. That would be negative square root 3 over 2. Cosine theta equals x coordinate. Look just at your x here. It's negative square root 3 over 2 and negative square root 3 over 2. So what angle gives us that x coordinate? And that's what that cosine theta is asking. Cosine of what angle gives you an x-coordinate of what's listed? That would be 5 pi over 6 and 7 pi over 6. Those are all the solutions to that equation on the interval from 0 to 2 pi because we looked at the entire unit circle. We didn't restrict it. We're not really using cosine inverse here. We don't have to create a one-to-one function. This is not one-to-one. What this is giving us two inputs that give us that particular output for this. And that's okay. These are all the solutions that are going to solve that equation. We can't really afford to be one-to-one here because we'd be missing some of the solutions on the interval of 0 to 2 pi. So I hope this makes sense. I hope that you're understanding, isolate your trig function, use your unit circle on the entire 0 to 2 pi. This will give you all the solutions for that interval. Don't forget to do things like a plus and minus when you're taking square roots, because that's going to lead to more solutions. We don't want to miss them. All right, let's take a look at one more for now. 3 tangent squared theta equals 1. Let's start all of these by isolating our trig function if we can. Now, we are going to run into some where we need to factor or do a substitution or use an identity, and we'll get to those in just a bit. But the basic ones where you're only seeing one trig function or where you can combine your terms, do it. In this case, since we only have one trig function, we're going to isolate it directly. We're just going to divide by 3. Now we're also going to take a square root. Every time we put the square root on the paper, we really need to be putting a plus and minus. Now sometimes it's not relevant, but it certainly is here. So we're taking a square root of both sides. We're going to get tangent theta on the left-hand side and positive and negative 1 over the square root of 3 on the right. Square root of 1 is 1, square root of 3 is square root of 3. You can leave it like that if you can find the angle that way. And some people can. Some people it's really nice to do that. If you're using a table, typically this will be rationalized as square root 3 over 3. I hope you can see that we're going to get 4 solutions again. So we're going to find the 2 angles on 0 to 2 pi where tangent theta equals the square root of 3 over 3. That's y over x. And the same thing for tangent theta equals negative square root of 3 over 3. My opinion, it's perfectly acceptable to use a table for this. If you're going to look at this and go, hey, tangent of what angle gives me this particular y over x relationship, this ratio, that's fine. If you're really good at a unit circle, it's not horrible. So when we take a look at this, we just need to understand that we're going to I really honestly think about it this way, but you see that on your table. That's why I gave you both of them. So we want to take a look at what would give us 1 over the square root of 3, or when you rationalize square root of 3 over 3, y over x gives us that. Well, that's going to be for positive 2 different angles. We're going to have here 1/2 divided by square root of 3, remember y over x. 1/2 divided by square root of 3 over 2 is going to give us 1 over square root of 3. So this is going to be pi over 6. It's also going to be the negatives. Negative divided by negative gives us a positive. So that would be negative 1/2 divided by negative square root of 3 over 2. That would also give us 1 over the square root of 3. And rationalized, it would accomplish this for you. So there's 2 angles, pi over 6 and 7 pi over 6. I hope that you just saw, so I hope you see something right now. I hope you see that if you take pi over 6 and you add pi, half a rotation, you're going to get exactly the same thing. Why? Well, the period of tangent is pi. And so we should be expecting that, and that's exactly right. So these values are all the same on quadrant 1 and 4 if you take pi and just add to it. You're going to get the same exact tangent every time. Even the signs are the same, positive and positive for tangent. Same thing would happen here. We're going to be in different quadrants. We're going to be in 2 and 4. So we're thinking of this, all right, now tangent of what angle is going to give me this y over x that yields negative 1 over square root of 3 from here, or negative square root of 3 over 3 if you rationalize it. Well, that's going to be the same thing, that 1/2 divided by a square root of 3, but we need opposite signs to get the negative. So I'm thinking 1/2 divided by negative square root of 3 over 2, and then negative 1/2 divided by positive square root of 3 over 2. And notice those are also pi away. So pi radians away from one another. So 5 pi over 6 is going to give me that, as is 11 pi over 6. I think tangent is probably the most difficult because you have to compare a y over x. It's not just a y coordinate or an x coordinate, it's y divided by x for our coordinates. So I hope that's making sense. I hope you're seeing that. Isolate, use your unit circle. Do not forget to take plus and minuses when you take a square root. That's a real big deal. So we're gonna come back. I'm gonna start making them progressively a little bit harder. We're gonna do a ton of examples, but I'm gonna make them very concise. I'm gonna go quickly through them just to instill the proper techniques for you. Let's keep on rolling. So we're going to continue solving some of these trig functions. I'm going to show you what to do when the argument of your trig function is not just theta. So how do you deal with that? We'll talk about exactly what that means and how you fix it. We'll use a substitution, and then I'll tell you that 3, if you remember from our graphing, that cuts, well, your period. It cuts your period into 3 parts. It makes it shorter, and so it's going to cycle more often on a unit circle. We're going to think of this as cutting a unit circle, honestly, and then we'll add to it or not add to it, depending on what that value is. The other thing is, what we're going to do for the rest of our examples is just find the solutions that are on that interval from 0 to 2 pi. That's what we did in the last few examples just before. I also think I had a mistake. If I'm thinking back to it, I think I actually had an equal sign right there. If I did, that was an error. And the reason why it is because 0 and 2 pi will yield the same exact solutions on that unit circle. And so what we don't want to do is have this issue where 0 and 2 pi give us the same exact solution. So we're excluding the 2 pi typically. So we go, yeah, set equals 0, include that, but not the 2 pi. That would double up some of our solutions. We don't need that. So anyhow, let's go on and solve some of these. So sine of 3 theta equals negative 1. What in the world do you do with that? Use a substitution. So what we're going to do is we're going to trick this problem a little bit. We're going to say, hey, let's call that 3 theta, let's call it alpha or something. So just something different. And let's solve it as if it's just a typical angle. We'll use the unit circle, won't be that bad. Then once we solve this on that particular interval, what we're going to do is we're going to divide everything by 3. So we'll substitute back, just a basic substitution, and it solves it really nicely. So step number 1, make sure that we can substitute for whatever that angle is to give us something easier to work with, something we can find on a unit circle. So I'm going to call this 3 theta something different like alpha. So we can say sine of alpha equals negative 1. Now, let's treat alpha like our angle and do exactly the same thing here. So sine of alpha equals negative 1. What that's asking for is, give me the angle so that the y-coordinate is negative 1. Sine of what angle gives me a y-coordinate of negative 1? That's going to be just 3 pi over 2. So in this case, we don't get 2 solutions here. That typically happens with our quadrant angles because we're not in a particular quadrant right in the middle. We don't have this like symmetry going on that we do with cosine, our x coordinates, and sine, our y coordinates. So we don't have that there. We're just going to get 3 pi over 2. Sine of 3 pi over 2 is negative 1. That's exactly what we're talking about. Now, here's the thought process. Because that 3 is going to cut, it's going to cut your 2 pi. It's going to cut this unit circle in thirds. It's going to make it shorter. This is going to cycle 3 times on that period. And so what we really, you can picture it, you can picture sine doing this, and if we shorten it over the same period, it would hit negative 1 more times because it's cycling faster. That's precisely what's going on right now. Hope that makes sense. It's going faster, and it's going to hit this value more times because of it. So here's what to do. Whatever number this is, just add 2 pi until you get that many cycles. So we want 3 cycles here. So this is one of them. Add 2 pi to it. Why? Because 1 full rotation will give you back the same y coordinate. Add another one, because 1 full rotation is going to give you back that same y coordinate. And this will cycle 3 times, divided 2 pi by 3, 3 times within that interval of 0 to 2 pi. Because we want to find all the solutions from 0 to 2 pi, we're going to have to do that. So whatever number this is, add 1 less 2 pi to that, 1 less iteration of adding 2 pi. So 3 pi over 2, cool. I'm going to add 2 pi. I'm also going to add 4 pi to it. So this is going to create 1 cycle, 2 cycles, 3 cycles on that 0 to 2 pi. We know that's going to happen because you took 2 pi, you divided by 3. It's going to cycle 3 times on that particular interval of 0 to 2 pi. Because we're looking for all the solutions there, just add 2 pi until you get 1, 2, 3 to match the 3 right there. That's the easiest way I can explain it. 1, 2, 3 for that number. Add 2 pi until you hit whatever that number is, 3 or 2 or 2, or don't add it all for that one. Actually, it's going to be something that we have to cross out. So we're going to show that. So if I take 3 pi over 2 and I add 2 pi to it, that's like 4 pi over 2. Well, that's going to be, let's see, 3 pi over 2 plus 4 pi over 2 is 7 pi over 2. Now, don't let this confuse you. I'm talking about adding 2 pi to this number and 4 pi to that number. So you can do it this way. You can add 2 pi, go back to here, add 4 pi, or just add 2 pi and then add 2 pi again. So another 4 pi over 2 would give us 11 pi over 2. Now, if you're thinking, wait a second, that's way outside of that interval. That's exactly right. And that's because we're not talking about theta. What's going to happen in just a moment? Well, we're going to say, hey, remember like that one time, like 5 minutes ago, where we set alpha equal to 3 theta? Well, this alpha, we're going to replace that with 3 theta, and then we're going to divide everything by 3. And what that's going to do is pull all of these back under 0 to 2 pi. It'll also give us all the solutions from 0 to 2 pi. If we hadn't have done that, if we had not have added those and got these things, well, then what would happen is that we would be missing some solutions on 0 to 2 pi. We shorten it actually. We shorten the period. We shorten that cycle. So it's going to happen more often on 0 to 2 pi. Add up until you get that many cycles, and then do your substitution again. So replace it back. So now that we have that, we can say 3 theta equals all of those values. Alpha is 3 theta, so 3 theta equals all 3 of those. If we divide all 3 of those by 3, we're going to solve for theta. That's kind of cool. So we kind of trick the problem. We call this an easier angle to work with. We solve it, understanding that that's shorten this. It's going to happen more often on 0 to 2 pi. How many times more often? Whatever that number is. So once, twice, 3 times. Just add to until you get that. Now divide everything by 3. And if we do that, remember that dividing by 3 is like multiplying the denominator. So when I divide by 3, we're going to get 3 pi over 6, 7 pi over 6, and 11 pi over 6. Yeah, we should simplify that. So 3 pi over 6 is really like pi over 2. Just check your work. Just check it real quick, just to make sure you get it. If I plug in pi over 2, this would give me 3 times pi over 2. Well, wait a minute, that's 3 pi over 2. That's right there, and that is -1. Notice how all of these solutions are between 0 and 2 pi. So even though these were outside of it, when we divide by 3, it pulls it right back down. Furthermore, these are all the solutions on 0 to 2 pi. This is it. This is our entire solution set. And that's kind of nice. That's really all that we do. We're going to do the same thing with tangent of 2 theta. So tangent of 2 theta equals -1. We're going to go through the same exact process. Let's call the angle something different. Call it alpha. So tangent of alpha equals -1. It's still an angle. We're still using the same thing. We're still using the unit circle, actually. So we're thinking about it. Tangent of what angle gives me -1? Use your table. Use y over x on unit circle. I like it that way. I mean, I'm just used to it. You can do whatever you want. So I'm thinking, what angle, tangent of what angle gives me -1, comparing y over x? That's got to be in quadrants 2 and 4. That would be, that's -1. Square root 2 over 2 divided by negative square root 2 over 2 is 3 pi over 4, and also 7 pi over 4. Now we're going to go look back just a moment. We're going to look back and say, okay, what was this? What did that do? That shortened this interval of 0 to pi by 2. That's what that did. Now, we do understand that the period of tangent is pi. I get that. So it's shortening that too, but because we have 2 periods on 2 pi of tangent, it's just shortening both of those, really. And so we're going to add our 2 pi to both of our solutions. Just make sure that you have that many cycles. So add it until you hit that. So I'm going to go ahead and add 2 pi to both of our answers here. So alpha is going to give us 3 pi over 4. Let's see, 3 pi over 4 plus 2 pi, that's 3 pi over 4 plus 8 pi over 4, that's 11 pi over 4. And 7 pi over 4, let's see, 7 pi over 4 plus 8 pi over 4 is, oh man, 15 pi over 4? Now there's a couple of those that are more than 0 to 2 pi, and they are a little bit out of order. It's not such a huge deal, but we do want to try to put them in order if we can, from smallest to largest. But what's going to happen? Well, because we used alpha here and not 2 theta, we're going to substitute back. So we said tangent 2 theta, now let's call it alpha. Let's solve this as if that's our angle. Okay, there's 2 answers there, but because we know we're shortening that 0 to 2 pi in half, what we're going to do is we're going to take and add up until we hit that many cycles. So here's 1 and 2 for each solution. 1 and 2. That's 1. This is the 2 for this solution, 2 cycles, and 2 cycles for that solution. So there's 4 total quasi solutions here. We're not to theta, we're still in alpha. Now we're going to do our substitution. So we're going to say, hey, alpha really is 2 theta. Let's call it that. And if we divide everything by 2, we're basically just multiplying our denominator by 2 if we divide. So it's going to be 3 pi over 8, 11 pi over 8, 7 pi over 8, and 15 pi over 8. We don't even need to simplify. That's fantastic. These 2 are out of order, but that is the largest solution that you have. It is just less than 2 pi. 15 pi over 8 is just less than 16 pi over 8, which would be 2 pi. So this is all the solutions on 0 to 2 pi. I hope you're seeing why it's working. I hope you're seeing how it's working, firstly, but then why it's working. Because that 2 cuts that 0 to 2 pi in half, really, or both periods of tangent in half, we're going to get more solutions that qualify in that interval when we're all said and done. It's going to cycle faster. And this is really the best technique that I found that'll do it. We just have to make sure that whatever solutions you're getting, if that number's more than 1, that you're adding up to that many cycles. So for 2, make sure you have 2. For 3, just keep on adding till you hit 3. Here's 1, 2, and here's 1, 2, and do it for every solution. Then when we substitute back, we're dividing or solving for that theta. It's kind of nice. All right, cosine of 2 theta equals -1/2, and tangent of theta over 2 equals square root of 3. I had those on the board before, we just ran out of room, so I had to erase them. So now we're going to solve them the same exact way. They're already isolated trig functions. That's fantastic, and we're going to sort of combine these ideas in just a moment. But whenever you have this argument, this angle that is not just theta, just substitute it. Solve the equation like normal and then put it back. The only caveat here is that that number is going to shorten your period. So it's going to happen more often on that interval for which we find all of our solutions on. So let's call 2 theta alpha. Cosine alpha equals -1/2 is asking what angle is going to give you an x-coordinate of -1/2. Well, x-coordinate of -1/2 would be 2 pi over 3 and 4 pi over 3. So x-coordinate -1/2 here and here. 2 pi over 3 and 4 pi over 3. Now, because our theta, or our alpha is equal to 2 theta, that 2 is shortening this. We're going to add until we get that many cycles, that many repetitions of this the function on 0 to 2 pi. So that shortens your period. Therefore, it's going to happen more often on 0 to 2 pi. And so we're going to show that. So we're going to add 2 pi. So here's 2 cycles on that particular solution. What that one is that's right here. So that's going to say I have this solution. If I go again, I'm going to hit back that. Same thing here. Here's my solution. If I go again around there, I'm going to hit right back at that point. So that's 2 cycles for each solution that you do. Not 2 total. Those are 2 unique solutions. We don't say, oh, there's 2 cycles. No. This is on the first cycle around. You hit the same x-coordinate twice. You get -1/2 on 2 different points on the unit circle in 1 revolution. We're going to go an additional cycle to make that 2. So here's 1, 2, and 1, 2. We're just going to add that 2 pi. So 2 pi over 3 plus 6 pi over 3, that's 8 pi over 3. There's 2 cycles as we want. It matches that. Make this match that many. And 4 pi over 3. Let's see, 4 pi over 3 plus 6 pi over 3 would be 10 pi over 3. Now that we have that, we're going to be very comfortable setting 2 theta equal to those and just dividing by 2. It's going to take everything that's outside of 0 to 2 pi and pull it right back in. So when we divide, you'll also notice these are really easy to put in order because our denominators are all the same. So I put these in order just to make it a little bit nicer. You don't really have to, it's just nice to see that. And then divide everything by 2, or multiply your denominators by 3. So 2 pi over 6, 4 pi over 6, 8 pi over 6, 10 pi over 6. Essentially, we're just really dividing. You could have done that too, dividing your numerators, same exact thing, or simplify. Those are your 4 solutions that you get here. Now notice, all 4 of those solutions are between 0 and 2 pi. There's nothing larger anymore because we divided by 2. That's why we add these extra cycles, because we know we're going to pull them back down. So I hope it's making sense to you. If you don't do this, if you don't add that, then you're going to be missing some. And it's really frustrating. Students oftentimes go, I got them. Then why am I missing some? Where do those come from? It's because you have to add those cycles because you're shortening it, and it fits more cycles on that particular 0 to 2 pi period you're looking for. That's why it is. Let's take a look at that one. One thing to notice is that this is theta divided by 2, not times 2. What's going to happen here? Don't add any of this. In fact, this is lengthening. This is lengthening a period. It's going to happen less times on 0 to 2 pi. In fact, some of the solutions we get here are going to be outside of that, or outside the interval. We're going to have to really look at it and say, yeah, this doesn't fit. You can see this bear out for a second. Same technique works with isolate our trig function. We're going to call the inside alpha. So tangent of alpha equals square root of 3 says, what angle is going to give me this y over x relationship of the square root of 3? Well, that's going to be a square root of 3 over 2 divided by 1/2. So the 2's cancel. That only happens where y is square root of 3 over 2 and x is 1/2. Both positively or both negatively for the positive square root of 3 that we get. So that's pi over 3 or 4 pi over 3. So those are the two solutions that we have there from our unit circle. Typically what I'll do if I'm adding other periods to it is I'll show that these are two different alphas. Or, well, I'm sorry, two solutions to the same alpha, but I'll show that differently so I don't forget to add cycles to it. In this case, I'm not doing that, which is why I wrote it the way I did, but maybe it's better to do it this way. So, should I add anything to it? No, not if you really understand what's going on. That is making more of them fit, shorting. Remember, this is a horizontal compression. It's making more of them fit into 0 to 2 pi. That is divided by 2. It's a stretch. It's lengthening this. There's going to be less of them that fit. And so I'm not going to be adding anything to this. In fact, this is it as far as our solutions for alpha. We don't want to add more because what's going to happen is we're going to start multiplying all of these by 2. Even some of the ones that fit in 0 to 2 pi now are not going to later. And so we really have to be careful on that one. So if you have something divided, something less than 1, don't add any cycles to it. If you have something more than 1, yes, add at least 1 cycle to it, to all your solutions. So we're saying less than 1, don't add any cycles to our solutions. Now we're ready to set this equal to our theta over 2. Now, we're not dividing by 2, we're multiplying by 2. That's going to be 2 pi over 3 and 8 pi over 3. Oh, pay attention to that one. How much is 2 pi over 3? Well, 2 pi over 3 is right there. That's fantastic. That works just great. But 8 pi over 3, let's see, 3 goes into 8. 2 times with a remainder of 2. That's 2 pi over 3 plus... Sorry, it's 2 pi plus 2 pi over 3. That's a problem because this is outside of that interval. So if you're just looking for the solutions between 0 and 2 pi, you need to see that that's more than 2 pi. 8 pi over 3 is like 2 pi plus 2 pi over 3. This is outside of that range, or the domain for what we're signifying that theta is. So I hope that makes sense to you. Hope you're really getting that if we have a number in front of theta that's more than 1, you're adding cycles. Just match it up with that number. If you have one that's less than 1, you're not doing that. Do not do that because you're already probably going to cross some out there. Once you start multiplying, it's going to grow this. It's going to make them outside of 0 to 2 pi. So I hope I explained that well enough for you. We're going to come back and do a little bit more complicated, getting a real good handle on this. Let's keep right on going. So we've got secant of 3 theta over 2 equals negative 2. Don't be afraid to use reciprocal functions. So if secant of 3 theta over 2 equals negative 2, use cosine. There's no problem. We're not dealing with the inverse functions right now. We can easily do that. Cosine's a bit easier to deal with because it directly matches to most unit circles that we have. You can use a table too, that's fine. Typically what I'm going to encourage is, yeah, just go ahead and use cosine for this. So if secant of 3 theta over 2 equals negative 2, then cosine of 3 theta over 2 equals the reciprocal of negative 2, or negative 1/2. Now we're set. Now we're going to call this alpha. We're going to solve this just like we normally did. So cosine alpha, just letting alpha equal that weird angle in there, equals negative 1/2. This asks, since cosine is related to the x-coordinate, what angle gives me an x-coordinate of negative 1/2? We've done this a couple times already. That's going to be, well, let's see, 2 pi over 3 and 4 pi over 3. What in the world would you do with 3 theta over 2? Evaluate it. Is that more than 1, or is that less than 1 in front of that theta? So 3 over 2, well, that's 1.5. So if you're really smart about it, you add 1 cycle to this, but you don't to that. Now, if that's confusing, you go, what in the world? Why not? That's the bigger one. The next one is going to be outside of 0 to 2 pi. If that's too confusing, add it to both of them, but understand that you're probably going to get something outside of 0 to 2 pi. So that's not yet 2. It's not shortening enough for 2 cycles to fit into 0 to 2 pi. This one's going to, that one's not going to. I'm going to show you that right now. So anything more than 1, add a cycle. If it's more than 2, add 2 cycles. If it's more than 3, add 3 cycles. So I'm going to add 2 pi and 2 pi. That's another cycle around that unit circle. So 2 pi over 3 and 4 pi over 3, that's fine. That's what this angle would be for cosine theta equal negative 1/2. I'm saying that's more than 1. I'm going to add 1 cycle. I really don't need to do that one, but I'm adding it again anyway. So our alpha is going to be 2 pi over 3. Let's see, 2 pi over 3 plus 2 pi, that's 6 pi over 3. That's the same thing as 2 pi. That would be 8 pi over 3. And 4 pi over 3, that would be 10 pi over 3. If I add that 2 pi, that's like 6 pi over 3 plus 4 pi over 3, it's 10 pi, well, not over 6, 10 pi over 3. Now, some of those are obviously more than 0 to 2 pi, but we haven't substituted back yet. So we're going to say, hey, because alpha is 3 theta over 2, these are all equal to 3 theta over 2. So I did switch these, but notice something. We're going to solve this for theta. We're going to multiply everything by 2, divide everything by 3. This one, and this one, and this first one are all still going to be in 0 to 2 pi. That one's not. That's going to be just outside of it. And so we're going to cross it off because it's not going to fit the interval for what we're defining our theta as. And that's what I was saying for numbers that aren't integer, well, whole numbers, like 2 or 3, if it's like 1.5 between 1 and 2, well, then you have to add 1 cycle, but it's typically just to the smaller of those 2 solutions. That usually works if it's, there is obviously some breakover. So if it's just barely less than 2, well, then you're probably going to add it to both. So a fail-safe is if it's more than 1, add 1 cycle. If it's more than 2, add 2 cycles. And that will keep it very nice. Just be careful to check your work and cross out anything that's outside of the interval for which you're trying to find solutions. So here we're going to multiply everything by 2 and divide everything by 3. So 4 pi over 9, 8 pi over 9, 16 pi over 9, 20 pi over 9. That's less than 2 pi, that's less than 2 pi, that's just less than 2 pi, that's not. That is, let's see, 9 goes into 22 times with the remainder 2. That is more than 2 pi, and this is what I was talking about, this is what we want to cross out. I hope that makes sense. I hope you're seeing that I need to add cycles Like I was saying, for stuff like 1.5, you add just the first one. But if it's a weird number and you're not sure, just add a cycle to both, understanding that you might have to cross them out later. Just check your work. Just make sure that all of these are within the interval you're trying to find solutions for. Let's go ahead and do one more. So square root 3 cotangent theta equals 1, or plus 1 equals 0. Solve it for your trig function. Isolate that first, and then start doing your reciprocals if you have one of these functions you don't really want to work with all that much. So cotangent theta equals -1 over square root 3. I'm just isolating that trig function. Now, before you rationalize, reciprocate for tangent. We don't want to rationalize then reciprocate and then have to rationalize again. That'd be kind of silly. And so if cotangent theta equals -1 over square root 3, then tangent theta equals negative square root 3. This is kind of nice. We don't have any odd angle in there, nothing that we have to alter the period for. So we're just going to look on our unit circle and say tangent theta equals negative square root 3. So what angle gives me a y over an x that yields negative square root 3? It's got to be in, oh man, I hope you see it. It's got to be in quadrants 2 or 4. Tangent is negative in 2 and 4, not 1 and 3. So in 2 and 4, we'd say, I want the square root on the numerator. I want a 1/2 on the denominator. That's got to be positive square root 3 positive square root 3 over 2 over negative 1/2, 2 pi over 3, or negative square root 3 over 2 divided by 1/2, 5 pi over 3. So 2 pi over 3 or 5 pi over 3. There's no manipulating our angle here. These are all the solutions between 0 and 2 pi because we found it. We literally looked at the unit circle and found all of them. So I hope this is making sense to you. We're going to come back to a few more. We'll eventually start getting into something that we have to use identities for. All right, 2 really quick ones. We're going to do this one, solve it for sine, really quick, and then we're going to take a look at what in the world you do with 3 theta plus pi over 18. It's going to end up being the same thing, but just be careful on some of the times you can run into issues with adding too many cycles or too few because of what you're adding there. So you have to massage that a little bit. So whenever we're solving something, no matter what it looks like awkwardly, and this is why I'm giving this problem, is if there's only one trig function, you can isolate it. If there's not, try to combine it. And if you can't, then you need another technique. So no matter how ugly that looks, if there's one trig function, isolate that trig function. So we're going to subtract 3 square root 3. That'll be -2 square root 3. If we divide by 4, we're going to get negative square root 3 over 2. And this is kind of nice. This says, what angle gives me a y coordinate? Remember, sine is y coordinate. What angle gives me a y coordinate of negative square root 3 over 2? Y coordinates are 4 pi over 3 and 5 pi over 3. Because we haven't altered that at all, our angle at all, those are all the solutions on the interval for where we're looking for our solution. So that's it, we're done. One trigonometric expression, solve it correctly, isolate that trig function. Now, what about some of those angles that look really weird? Try the same thing. So I was saying just a minute ago that sometimes we run into some issues where we will miss a solution or we'll get an extra solution with a certain interval if we add 3 cycles because of that plus pi over 18. Most times that doesn't happen, but if it does, then you can always try adding an additional cycle and seeing if that's going to give you another solution in 0 to 2 pi. So let's try that here. So alpha equals, just call that whole thing alpha. Man, that looks a lot better. So sine of alpha equals 1 says, hey, find me the angle that gives me a y coordinate of 1. That's going to be pi over 2. And that's it. There's only one solution on 0 to 2 pi that has that particular y coordinate of 1. So alpha equals pi over 2. Now, because that is a 3, we want 3 total cycles. If that had been a 4, we'd want 4 total cycles. This is one solution on that first cycle. We need another solution on another, and then another cycle, so 2 additional cycles. We're going to add 2 pi for that. Then we're going to add 2 pi again, or add 4 pi to our original solution. So let's try that now. All right, so we got pi over 2. If we add 2 pi, that's 4 pi over 2, so 5 pi over 2. If I add 2 pi again, or add 4 pi to pi over 2, either way you want to go, it doesn't really matter. So 2 pi to this is that one. 4 pi to this, or 2 pi to that. So that'd be an additional 4 pi over 2, that's 9 pi over 2. Now that's way outside 0 to 2 pi, but remember, we're about to subtract pi over 18 and then multiply by 3. So since we solved for alpha, we know what alpha is. And now we're going to, remember order operations, we're going to subtract pi over 18 before we divide by 3. So when we subtract pi over 18, so pi over 2, that's like 9 pi over 18. So 9 pi over 18 minus 1 pi over 18 is 8 pi over 18. Five pi over 2 be like 45 pi over 18. That's 44 pi over 18 if I subtract 1 pi over 18. $81 pi over 18 for 9 pi over 2. So 9 pi over 2 is like 81 pi over 18. Minus 1 pi over 18 is 80 pi over 18. Now, of course, all of these are going to simplify. So we can do that now, we can do it later. It kind of matters. I mean, it's a little bit nicer to multiply by the denominator by 3 once you've simplified. So I'm going to do that now. I'm going to divide everything by 2. And lastly, we're going to divide by 3. So multiply our denominators by 3. That's going to be all over denominator of 27. So 4 pi over 27, 27 pi over 27, 40 pi over 27, and that's it. Now, one thing can happen, I was just talking about this a little while ago, is that if you have a large enough angle that's subtracting, you could fit another, because that's a phase shift, right? What that is a shift of sign to the left. It's to the left. Pi over 54. So it's a really small shift, but this is shortening and shifting. And so what's going to happen here is you might fit another solution in 0 to 2 pi. If that's the case, what you would want to do is add an additional cycle to that. If that's a large enough shift, you might get that. You might actually have a negative here too if you shift far enough. So just be careful on that one. Typically this works just fine. Remember, that number is how many cycles you want in general. Adding a phase shift to it or subtracting any phase shift can alter that just a bit. Just mind that. Just be very careful that you could be outside of 0 to 2 pi. You might have to add an additional cycle. That's really all there is about it. That's about as hard as I can make an angle there for you. I hope that is making sense to you. I couldn't resist. I had to do it. So I added another cycle just to show you that this is pretty close, but it's too much. So if we add one more cycle, we get 13 pi over 2. If I subtract pi over 18, I get 1/16 pi over 18. And then if I divide both by 2, 58 pi over 9, and then divide everything by 3, we get 58 pi over 27. 27 goes into 58 2 times and then some, but just a little bit. Had I subtracted a bit more than that, then I would have been able to fit another cycle in there. So I hope you're seeing that. So if this is large enough and you're not sure, you're like, I don't know, then add an additional cycle. So just, hey, here's 1, 2, 3, and you go, well, I don't know about that one. Add another one. It doesn't really hurt all that bad. It just means that you'll get an extra solution in there and it doesn't fit inside the interval that you're looking at. And that's really all there is to it. These two are tricky, and I throw them in here because a lot of students mess these up. A lot of students really have a problem understanding why there's two solutions when cosine inverse only gives you one solution and sine inverse only gives you one solution. So if you need to find all the solutions on that interval, 0 to 2 pi, cosine inverse and sine inverse will not do it completely. It'll give you half. It'll give you the one-to-one solution. It'll give you the solution for cosine from 0 to pi. For sine, it'll give you the negative pi over 2 to pi over 2. It'll give you that. Remember what inverses do. Inverse functions are one-to-one functions. They will give you one solution here. So if you need to find both, there's a way around that. So I'm going to show you how to find both solutions to cosine theta equals 0.6. Even though 0.6 is not on a unit circle, how to actually do that. So let's start off with the thought that cosine theta equals 0.6. I would look for a unit circle solution. It's not on there for 0.6. So how do we solve for theta if we're not on a unit circle? Well, we'd use cosine inverse. So cosine theta equals 0.6 if theta equals cosine inverse of 0.6, or cosine inverse of 0.6 equals theta. And that's the same thing. Now, your calculator will give this to you. But you must remember that inverse functions only give you one solution out. They have to. So cosine inverse of 0.6 is going to give you around 0.927. And you go, great, I'm done. Not really. What this means, what this is this says, oh man, I hope you remember it. It says, what is the angle that gives me an x-coordinate? Cosine is always an x-coordinate. So cosine of what angle gives me an x-coordinate? What angle gives me an x-coordinate of 0.6? Where is 0.6? Where is an x-coordinate of 0.6? If that's 1, 0.6 is about right there. On a unit circle, that is the angle they're giving you. Why is it that angle? Well, because cosine inverse, man, I hope this is making sense. This is the biggest thing here, is cosine inverse only works from 0 to pi. That's it. It's just going to give you that one angle. This is an x value or x coordinate of 0.6, about. That's the angle they're giving you, what, 0.927 radians. This is 0.927 radians. That's exactly what that is. It's less than 1 radian, it's less than pi over 2 radians, it's 0.927 radians roughly. But look at this. There's another point on the unit circle that would have that x value, that x coordinate of 0.6. This would be 0.6 comma some y, and this would be 0.6 comma some y. Therefore, there's another angle there. Now, how do we find it? These angles will have symmetry. So this right here would also be theta. However, we can't have a negative angle on 0 to 2 pi, can we? Because that's 0 is the smallest value. I don't want a negative angle that's outside my interval. So here's what to do with that. If this angle's theta and this angle has symmetry is also theta, take 2 pi minus your angle. So imagine you go all the way around and go, oh, I went too far. Back up. How much would you back up? You back up theta. So cosine inverse will give you a solution, an angle out on the interval that it's defined for. For cosine inverse, that's 0 to pi. So it's going to give you that angle. No problem. Use your calculator, you're good to go. But then draw a picture of it. Because cosine is talking about the x-coordinate will be the same here and here. Remember, it's the x value here and here. So we go here, great, calculator. Okay, imagine we go all the way around and we've gone too far, back it up, that symmetrical angle. This would be found by 2 pi minus whatever that angle is. Well, what's that angle? We found it. .927 is the number of radians. Wait a minute, 2 pi is in radians, so 2 pi minus 0.927 is going to give you another angle. Specifically, it's going to give you this angle that goes all the way from here to here. That's the other angle that we would have. It's about 5.36. Now, 5.36 radians. Notice that that's just under 2 pi radians. 2 pi radians is like 6.28 or so radians. So that's below that. That's exactly this angle less than that. So I hope that makes sense. It's a little weird. I know that it's weird. Just remember what inverse functions do. They're only going to give you one solution and only on the part where it's defined. So for cosine inverse that's 0 to pi, we need to understand that cosine deals with the x coordinate. There's always going to be two x coordinates on a unit circle that are the same. That's positive, quadrant 1, and negative, quadrant 4. Negative is a better way to say is above and below the x-axis in quadrant 1 and quadrant 4. And then we say, all right, let's just subtract that symmetrical angle to find it. Something very similar happens with sine theta equals 0.4. So when we're thinking sine theta equals 0.4, we try looking in a circle and 0.4 is not on there. So what angle gives me a y coordinate of 0.4? I have no idea. I don't know. But I do know that we can do an inverse. So if it's not on a unit circle, use sine inverse. Now, what in the world does that mean? Well, if we're thinking about this, a y coordinate of 0.4 would have to intersect this horizontal line at 0.4. That again is going to give me two angles, but check it out. Sine inverse will only give me, oh man, I hope you remember, sine inverse only gives me answers from negative pi over 2 to pi over 2. So it will give me this angle. This is from negative pi over 2 to pi over 2. It'll give me the one solution that's on that interval that has a y coordinate of 0.4. It'll give me that particular angle. I hope that makes sense to you. Sine inverse says the angle that gives me this y coordinate on this particular interval, so right there, is theta. And this would give you this, it would give you this angle of about 0.41 radians. So this angle is about 0.41 radians. But we're smarter than that. We understand that, hey, a y coordinate will happen twice on a circle if we're not on a quadrant angle. So y coordinate would happen 0.4 here. It also happened 0.4 here. This would have a y coordinate of 0.4, that same height. Only how do we find that angle? Well, a very similar way as this. This will have symmetry on that angle. So this is also theta. So how in the world would we make it to this particular angle going from an initial side to that terminal side? That's the angle that we want. Well, imagine going a little too far. You go, oh, I'm going to go all the way to pi. Oh, I went too far. What would you do if you went too far? You'd subtract some. How much would you want to subtract? Theta. So if we said this is not as far as pi, it's just theta less than that. We went too far, go back a little bit. So we'd have one angle of 0.41 radians and another angle of pi minus about 0.41 radians. That's approximately 2.73 radians. You go, what's 2.73 radians? Remember what pi is. Pi is 3.14. This would be approximately 3.14 radians. We're not quite there yet. We're 0.41 radians less than that, 2.73. So it's a little weird. Just remember what sine and cosine do. Cosine is x-coordinate. You're probably going to have two of them this way. Subtract 2 pi minus that angle. Sine is y-coordinate. You have two of them this way. Take pi minus that angle for the ones that are not on the interval for which sine inverse and cosine inverse are defined. For tangent, all you really have to do is add pi. So that's the period of tangent is pi. So if you run into that and you're like, okay, I have one solution, where's the other one? Just add pi to it and it's usually pretty good to go. So we're gonna come back and start using some identities to solve some of these equations. It gets kind of fun. Some substitutions and things where you can't isolate the trig function exactly. So we're going to deal with a few problems that you can't isolate a trig function because there's more than one of them, or the same one that's raised to a power. You just can't isolate it directly. If that's the case, you need another technique. So here's the things to look for. Number one thing you look for is, can you factor it? If you can factor it, if you can use a substitution to allow it to be factored, if it's already factored, that's great. We can use the zero product property. If not, we're probably going to have an identity. So the number one thing you try to do is isolate your trig function or combine terms to isolate it. Let's check that. Can you combine those? No, because one's got a power 2 and one doesn't. That'd be like x squared plus x. And you go, I can't add that. You can't add those trig functions either. But what you can do a substitution. Now, some of you who are very good at factoring, you can factor it just like that. It's not even a problem. But if you're struggling with this a little bit, remember that every time you have a power 1 here and a power 2 there, you can make a substitution of the inside thing. The inside thing here is cosine. Remember that this means cosine theta squared. So if we let's say u equal cosine theta, that lets us do this substitution. So if u equals cosine theta, all we're looking for a substitution is this thing and this thing to be the same, where this is 2 times that thing. That's all we really need. So let's go ahead and let's make that. Then cosine squared theta would be u squared. Because cosine theta is now u. We get cosine theta squared. Well, no, we called cosine theta u, so u squared plus u equals 1. Now, when we're factoring, we want to get everything on one side. We want to get in order, first term positive. And now that we have u instead of cosine theta, it's nice to do that. So we'll subtract 1. This is something that's really nice to factor. So we can do this. There's a lot of different ways. I've seen people factor. Any way that works is fine with me. I don't really care. This is going to be, let's see. If I do it my way, I always like to put my middle term here, first and last term, multiply, that's -2, add to the top, multiply to the bottom, and then take your a and divide, and simplify, and this will give you your factors. This is 1u, remember this is not x or anything, 1u plus 1, 2u minus 1. And we can continue to solve. This is what is beautiful about factoring, is that it creates a zero product property, something that's very nice for us. So we know zero product property says if you got a couple factors or several factors and they're equal to 0, every one of them equaling 0 has the opportunity to be a solution. So u equals -1 and u equals 1/2. Are you done? No, you are not. This is just in u. You don't want u. You want cosine theta. So because cosine theta is u, then cosine theta equals -1 and cosine theta equals 1/2. We don't have any awkward angles. We don't have to manipulate that. But if you did, at this time is when you'd say, if that was like 2 theta, call that alpha, then solve for alpha, and then you divide by 2. You'd give extra cycles in there. We don't have to do that. This, by solving with your unit circle, is going to give you all solutions on 0 to 2 pi. So cosine theta equals -1 says, on what angle is my x-coordinate -1? That's pi. Cosine theta equals positive 1/2 says on what angle are my x coordinates, is my x coordinate 1/2? Well, there's two of them. It's going to be pi over 3 all the way around 5 pi over 3. Those are the two angles where you have an x-coordinate of positive 1/2. These are all the solutions of that equation on that particular interval. And that's really all there is to it. So number one is try to isolate your trig function, combine some like terms if you can. If you can't, look for factoring. If you don't, you can actually factor this by subtracting 1, then going right down to here. Well, you'd have cosine squared and cosine squared. You have cosine and cosine here. If that's too difficult, that's okay if it is. Do a substitution. Just call the inside part u. Factor it and then put it back. We've done a lot of substitutions in many, many videos. This is just another one that we can now utilize. So getting everything on one side, factoring, then putting back your substitution. Just remember that if your angle is different, you have to manipulate that a little bit. Just add your cycles if you have to. Now, next one. Tangent theta minus 1, secant theta minus 1, multiplied together equals 0. Do not distribute this. I'm begging you. Please don't distribute that. If you have two factors, which you do, multiplied together, which they are, equal to 0, you win. This is fantastic because you can set each of those equal to 0 by the zero product property, the exact same thing that we did right here. Don't substitute, definitely don't distribute. This is easier than that. So tan theta minus 1 equals 0 by the zero product property. And secant theta minus 1 equals 0, again by the same property. And these, oh wow, now that we've done that, these are some basic trig functions. You can actually isolate that trig function. Just like here where factoring lets you isolate the variable easily, using zero product property lets you isolate the trig function easily. So adding 1 in both cases where tangent theta equals 1 asks, on what angle is your y over x giving you positive 1? That's pi over 4, and that's 5 pi over 4. So here pi over 4, and there 5 pi over 4. You can use a table for secant theta. So secant theta equals 1, that's fine. I will use a reciprocal and say secant theta, the reciprocal of that is cosine theta. So cosine theta would equal the reciprocal of 1. That would also be 1. Well, where is the x-coordinate 1? That would be on 0. So an angle of 0 gives you an x-coordinate of 1. Right there. There's a little blurb I said that I made a mistake at the very beginning of the video that I accidentally had an equals there. Notice how I don't want that because 0 and 2 pi would give me an x-coordinate of 1. I only really want one of those to be on that interval. So I'm going to choose the 0 and not the 2 pi. That's why we don't want to equals on both. So cosine of 0 equals 1, that's fantastic. So I have 3 solutions, pi over 4, 5 pi over 4, and 0. Hope that's making sense to you. Factoring is really nice. Don't distribute if you already have the zero product property. All right, we're going to do 3 examples right now that illustrate the important use of identities. Now, in trigonometry, when students hear identities, they go, oh my gosh, they're horrible. They can be. They really can. They're tough. I'm not going to sit here and lie to you and say, oh, they're a piece of cake. If you understand them, they're extremely useful. And when you get to calculus, like calculus 2 especially, we use a ton of identities. The better you are now, the easier that class is going to be, I promise. Also, some of the substitutions I've already shown you, and I will show you later, trigonometric substitutions are a big deal for Calc 2. You're going to get something called an integral, and you're going to have them by trig sub, integrals by trig sub, and a lot of students hate them. I'll teach them to you very, very well in Calculus 2, but it's a lot of your trigonometry, things that you do in calculus, stem from identities. And so I'm going to start illustrating how you use those. So next few videos, we're dealing with identities, just purely identities, for a long time. It's going to be a huge video. But Right now, we're going to start because we really only know a couple of them. We know some even and odd identities. We know the Pythagorean identity. We're going to use that right now. We use even and odd in the next example, and then tangent equals sine over cosine in the one after that. So, sorry, spoiler alert, I just ruined it. The whole thing. That's what we're going to do. But it's important for you to know where we're going. So here's how we start with identities. Number one, we try, well, and this is using identities, not exactly proving an eidetic relationship. We're using them to solve an equation. But number one, look at the hard side. What side looks harder? Well, that side looks harder. Start with that side. Try to make one fraction if there's fractions. Try to write everything as sine and cosine if it's not. It is, there's no fractions. Try to identify some identities that work with what you have up there. So I have sine squared, I have cosine squared, theta. What do I know about sine squared? Well, there's only one identity that I know of. The last one is this. Last one is, if you have all of one type of trig function, see if you can make it into that type of trig functions. Or the majority is like sine, make everything into sine. If the majority is cosine, make everything cosine. If you have cosine squared plus sine squared, that's 1, and that's fantastic. We're not there yet, but we do have this sine squared. I see a cosine, I see a cosine squared, I see a sine squared. This is kind of the odd guy out. I want to change this guy. See, that's a cosine squared and a cosine. Those work well together. That's fine. We can maybe factor that, but this does not. And so what we're going to do right now is we're going to look at that and think, what identity do I know that deals with sine squared theta? Well, there's really only one that we have right now, and this would be the Pythagorean identity. We did it many videos ago, but this is one of them. So I'm going to solve for what I want to get rid of. That's how identities can be used. So I want to get rid of sine squared, or at least change it. And so I'm going to solve this identity, which I know is true, for sine squared. Let's subtract cosine squared theta from both sides. So if this is true, which it is, then this is also true, which it is, which means you can substitute it. So I'm going to do that right now. I'm going to say, hey, sine squared theta is 1 minus cosine squared theta. So I'm going to change this piece down to that. So sine squared theta now changes to whatever this is based on the Pythagorean identity that we used to do it. So this is now 1 minus cosine squared theta. I had already a minus cosine squared theta. Now, it might seem like, how in the world did you know how to choose that one? Experience, and it will get better for you as you go. You'll start seeing some patterns. You'll start seeing, oh, right, okay, I have a cosine squared and a cosine. It looks like I'm probably going to factor that. In order to factor stuff, I need to make sure we all have the same type of term. So I want to change the one that's not cosine. How do I do that? Look for something that has a sine squared. So I pull out my identity sheet and I go, well, Pythagorean identities, that does it. That would change that into a cosine squared something or other. Hey, that would match the other cosine squared and cosine that I have. So let's do that. And that's sort of the thought process I go through. That's what I'm modeling right now. So I modeled that thinking for you on how you'd make it down there. Now, with that in mind, now we start trying to combine whatever we can. So if I combine my negative cosine squared theta minus cosine squared theta, that's minus 2 cosine squared theta. I can also subtract 1 from both sides, and those 1s are gone. One trap that students fall into is they try to divide. Do not divide by things that can equal 0. So cosine theta can equal 0, right? If we divide, then we're actually breaking a domain rule. We cannot divide by things that equal 0. It's going to eliminate some solutions. It's not good math, and we're breaking some rules. So instead of dividing right here, we're going to try factoring. So let's add 2 cosine squared theta on both sides, just to keep everything positive. So cosine theta plus 2 cosine squared theta. This is where we can factor. So the whole idea was, hey, this looks like factoring to me. So I see a cosine squared and a cosine. I'm going to try to factor that. This would not be great for us. So I'm going to try to change that into this thing. Use the Pythagorean identity. Okay, solve for the thing I want to replace. I got it. Let's replace it. No problem. Let's combine some like terms. All right. Hey, my ones cancel. Cool. Oh, I see some factoring now. Now we can factor out cosine theta. And now it's magic. Because we have a zero product property, we have two factors that are multiplied together to equal 0. We're going to set both of them equal to 0. So cosine theta equals 0. And 1 plus 2 cosine theta equals 0. We're going to solve both for 0. That's done. That we're going to subtract 1 and divide by 2. And now we use our unit circle. There's no funny angles going on. We don't have to add a cycle or anything. Cosine theta equals 0 when that angle is pi over 2. It also at negative pi over 2 or 3 pi over 2. So why not negative pi over 2? Because we're trying to keep in line with that. So from 0 to 2 pi. So our x-coordinate is 0 here and there. Pi over 2, 3 pi over 2. Our x-coordinate is negative 1/2 at 2 pi over 3 and 4 pi over 3. And that's it. We're completely done. Provided that we don't have any fractions where these solutions make 0 on our denominator. You're going to watch for that. We're done. These 4 solutions are within our domain of 0 to 2 pi. This is all the 4 solutions that satisfy that equation. I hope that's making sense to you. I know that this can be tough the first time you see it. You look at it and you go, oh, don't worry, you're going to get it. You're all very smart. If you've made it this far, you're doing great. So don't worry about it right now. This is an introduction into how to use identities. Okay, so just bear with me. I'm trying to get your brains wrapped around this concept. You will get it, and we're going to crush some identities in next video. But for right now, this idea of, oh, I can change what's here into something else by using identities is extremely powerful. So I'm going to show you 2 more examples on how that works. In the next video, we're going to talk about some pretty major identities. Let's talk about this one. It looks fairly straightforward, but there's some interesting things that happen here. And so we're going to take a look at it. So cosine theta equals negative sine of negative theta. Now, when we're taking a look at solving these things, of course, we're going to try to isolate our trig function, and we have 2 of them, so we can't really do that. There's no factoring right now. It's not apparent. It's not really cool that way. So we're going to have to use some identities. So if you can't isolate your trig function, if you can't straight up factor it or use a substitution, you're going to use something to change what's there. Use identities. It's the only way you can do it is by using identities to change what's there. Now, how do we do that? Most of the time, we start on a more difficult side. That's more difficult than this. So let's take a look at that. Negative sine of negative theta. Can we make it easier? That's the first thought that's going in my head. Can I make it easier? Well, every time we have a negative angle, you can change it. You see, all of these functions are even or odd. Sine happens to be an odd function. What that means is that opposite inputs give you opposite outputs. So sine of negative theta is equal to negative sine of theta. That was due to the oddness of sine. Cosine was even. We could just basically drop that negative inside there. Really, its opposite inputs are equal outputs, and so cosine of negative theta equals cosine of positive theta. That'd be easy. But this says you can change this part into negative sine theta. Can you see how a lot of students would probably make a sign error right there? That negative is there. Sine of negative theta is negative sine theta. So what's a negative negative? Opposite of negative is positive. So we have cosine theta equals sine theta. And you go, what in the world do we do with that? When does cosine theta equal sine theta? Now, you could actually look at a unit circle and say pi over 4. Where is the y-coordinate equal to the x-coordinate? Pi over 4. 5 pi over 4. You could do that. But there is a different way to go about it. If we go ahead and divide both sides by cosine, one idea is if you have sines and cosines, sometimes you want to get away from tangent and sometimes you want to get to tangent. I'm going to show you an idea right here that if we divide both sides by cosine, we can get tangent theta on the right-hand side. That's another identity for us. So dividing both sides, cosine theta divided by cosine theta is 1. Provided that we don't allow that cosine theta to be 0. That's the only issue with this. So that issue is, where's cosine theta 0? That would be pi over 2 and 3 pi over 2. Now, fantastically, the function that we're about to get, if I would have written this right, the function that we're about to get is undefined exactly where cosine is 0. Why? Because it comes from that, and that's fantastic. So sine theta over cosine theta. Now, why in the world did we do that? So I was looking at this thinking, let's make this easier. We did, using an identity, using the evenness there. Then I looked at this and said, I could probably do this, but it's easier if I make a function I'm used to. So I'm going to divide both sides by cosine, understanding that sine theta over cosine theta is tangent theta. That's much easier for a lot of students to look at and say, okay, hey, look at that. I can use my table, I can use my unit circle. Tangent theta equals 1. So on what angle do I have y over x being equal? Do you understand that that's exactly the same thing I asked right here? Like what angle is my y coordinate equal to my x? That's exactly what this is asking you. On what angle is my y over my x the same? That would be pi over 4, and that would also be 5 pi over 4. Because those both give you positive 1. Square root 2 over 2 divided by square root 2 over 2, or negative square root 2 over 2 divided by negative square root 2 over 2. Those are all the solutions on 0 to pi over 2, 0 to 2 pi that satisfy that equation. So I hope that makes sense. I know that identities can be tough, but I'm trying to kind of build that in your head that it's possible to change stuff to make our lives a little bit easier. So we'll come back with one more and then we're done. All right, last one. So tangent theta equals 2 sine theta. Now, when we take a look at solving these things, isolate trig function, we have 2 of them. Try to factor, there's nothing to factor. Make everything sines and cosines is a good idea, or make everything the same trig function if you can, if you think you're going to factor. So if I was to do that, if I said, here's my sine, here's my tangent, what one can we change easily? For sine, I don't really have an identity for that. But for tangent theta, I have an identity. We just use it. Remember that tangent theta is sine theta over cosine theta. This is another kind of rule of thumb for identities, is if you're getting stuck, change everything into sines and cosines and see what you can do after that. So I'm thinking, this side, I'm not doing much with that sine. There's no identity for just sine theta. There's sine squared, yeah, but I don't have that. For tangent, we do have an identity. So I'm thinking, I can't isolate, I can't factor right now. I have an identity for that one, not that one. Let's change that one. And inherently, we're going to change it to sines and cosines. So tangent theta is sine theta over cosine theta. Another idea is, if you can factor, it's nice to do. So let's get everything on one side. So I've thought, isolate, no. Factor, I can't. Use an identity, cool. Let's use identity on tangent, I've done it. Now I have some signs here. When we're solving equations, we like to factor things. So we get everything on one side, that's great. And now we're gonna try to factor. Can we factor anything? Well, sure we can. We can factor out sine. This has sine theta, this has sine theta. There's only two terms. If we factor out sine theta, we get 1 over cosine theta minus 2. And we can verify that by distributing. This would give us sine theta over cosine theta, hence the tangent, and minus 2 sine theta. And this is beautiful. This is why we like to factor, because this now created a zero product property for us. We have sine theta times this other term that equals 0. Let's set both of them equal to 0. Now, you can change that one, couldn't you? You could change that to secant if you really wanted to. This would be 1 over cosine theta. Oh, that's secant theta. That's the reciprocal function. You could do it, but you'll end up changing back to 1 over cosine or reciprocating that. So at some point, you'd have to change it back. So I'm going to show you both, kind of both ways here. So sine theta equals 0, no problem. 1 over cosine theta minus 2 equals 0. Let's solve both of them for their trig functions. So sine theta equals 0 is done. That looks really good. This one, well, we have to solve for cosine. Let's add 2. If 1 over cosine equals 2, then cosine equals 1 over 2. Just reciprocate both sides. Now, what if you had done it a different way? What if right here you said this is secant theta? Remember, 1 over cosine theta is secant theta. That's an identity for us. What if you'd done that? Well, then you would get secant theta minus 2 equals 0 by the zero product property. Then you would add 2. And then you'd say, oh, secant theta equals 2 if cosine theta equals 1 over 2, the reciprocal of that. And that's exactly where we find ourselves. Whichever one of these looks easier to you, do it. It doesn't really matter, you're doing the same thing. So whether you want to solve it directly for cosine, cool, you're going to get what happens when you use an identity for secant theta and solve it and use a reciprocal to get cosine anyway. Now we're ready to use our unit circle. We're almost done. So sine theta equals 0 says, give me the angle where the y-coordinate is 0, that's at 0, and that's at pi. Y-coordinate 0, y-coordinate 0 at 0 and pi. Cosine theta equals 1/2 says, give me the angle where the x-coordinate is 1/2. That's here at pi over 3. That's here at 5 pi over 3. X-coordinate of positive 1/2. So there's 4 solutions. That's all the solutions that's on that interval. There was no interesting angles to work with, no extra cycles to add. I hope that this has made sense. I especially hope you're seeing the utility of these identities. They're extremely helpful. I know they're challenging. Remember that like when you start learning this stuff, it's going to be frustrating. Frustration's okay. Frustration is our brain trying to cope with new information, and you're trying to make it fit. That's fine. You should expect that a little bit. But when you start getting angry at it, like, ugh, you go break your book in half. That's not okay. And you're going to get that way at some point. I know I do sometimes when I'm working on something that's just not making sense. That's when it's time to take a break. So take a break, step back from the math, let yourself calm down. What happens is when our brains get too wrapped up in that, it's like when you're having a conversation with somebody and you're arguing, and then someone starts yelling and you go, at that point no one's listening, you're not really learning, and that's what's happening here if you get mad at it. So once that happens, and it will happen, it's okay. Take a break, come back a little bit later. So frustration is okay. Anger, take a little break. So I hope it's making sense to you. I hope that helps you in some way. Next video, we're going to come back, and it's going to be a very long one. We're going to talk about how to use identities to prove relationships. So I'll see you for that. Have a great day.